and was packed with a lot of new information and concepts. I particularly liked that picture of Mars that you showed that was assembled by converting the Mariner 4 digital image into a hand color coded image, and that was really fascinating. These are bits and pieces we don't know, and we have to listen to a lot of talks like these to get all these like minute details which put the fun into the game. And moving on to the questions. So first and foremost, how do you think this new finding of yours, like it alters the picture of habitability we have? Does it paint a new picture on Mars?
It does, but I would like to impress this point that oxygen was not present on Earth when origin of life happened on Earth. So when life started on Earth, it was anaerobic life. When oxygen actually started coming out, it was actually a mass extinction event. So oxygen actually killed a lot of organisms at one point of time. So, I mean, if Mars did not have oxygen at one point of time, it doesn't matter. Life finds a way to thrive, right? So things can happen, but yeah, I firmly believe that it was not oxygen that might have played a role on Mars.
Hello, everyone. Hope you're doing great. I'm Priyabroto, and I'm the co-founder and director of IIREES. Today, Dr. Sumit Pathak, Ranjan Sarkar, and I will be your host. Sumit and Ranjan are postdoctoral fellow. Sumit is now working at IIT Kharagpur on lunar geology, and Ranjan is now at Max Planck Institute, Germany, working on geological evolution of Mars and the dwarf planet series. Before we begin, I would like to express my heartfelt condolence to all of those who lost their life, and I extend my sympathy to all who have affected by the earthquake that struck on southern Turkey on February 6th. I pray for a quick recovery, those who are all affected. And as you know, IREES is an India-based educational research initiative that aim to build a new generation of creative, passionate, and critical thinking natural scientists through transformative education and research support. We are now working actively on a 5-pillar academic model. The key objectives of our first pillar are to organize a hybrid lecture series, workshop, and outreach program on various scientific and socially relevant agendas. The vision of this program is to inspire the young generation towards scientific research by enabling critical thinking, sharing the latest scientific development, popularizing science, and building a vibrant research-minded community. Our second, third, and fourth pillar are designed to provide basic level, advanced level, and skill development courses on a few subjects that are uncommon in your syllabus but have a strong scientific temper. For example, Earth and Planetary Sciences, planetary remote sensing, origin and evolution of life, and the life extent in other planets, geochronology, numerical modeling and computer programming, and its application in geosciences, etc. The fifth pillar of IREES is designed to provide the research internship opportunity to the student community. IREES will provide necessary research support during the project period and help the student to write research paper, conference abstract, popularizing research article, etc. Earth and Planetary Science Seminar Series comes under our first pillar of core activity. I hope you enjoyed our first lecture by Dr. Kaushik Mitra on Mars. Today, on the auspicious occasion of the International Day of Women and Girl Child in Science, we are honored to have Dr. Mamta Chauhan from IIRS ISRO as our esteemed guest speaker. She will be presenting on the topic of geological exploration and planetary exploration of planetary bodies, especially Mars and Moon, with emphasis on ISRO's mission. I'm welcoming her also. So far, we have received a fantastic response, got registration from 15 different countries, 22 different states of India, and 65 different institutions. On behalf of IREES team, I thank you everyone. If you have any question, feel free to write in the chat box during the seminar or after the seminar, and please turn off your video and microphone during the presentation. Now, without wasting much time, I would like to invite Sumit to start hosting the rest of the session. Thanks for joining us today. Sumit?
Thank you, Piyoda. So, hello everyone. Myself, Sumit Pathak. I am a researcher at Department of Geology and Geophysics, IIT Kharagpur. I cordially invite all of you to the second lecture in our Earth and Planetary Science Seminar Series. Today, I am delighted to introduce our guest speaker, Dr. Mamta Chauhan. Dr. Chauhan is a scientist at Indian Institute of Remote Sensing, a Dehradun-based academic and capacity building unit of the Indian Space Organization, ISRO. She will discuss about the role of Indian ISRO's mission in the geological exploration of various planetary bodies in this lecture. Before we begin, a little background on our guest speaker. She earned her PhD in igneous petrology with a focus on carbonatites in Mayan igneous soot. After completing her PhD, she joined Space Application Center, another unit of ISRO in Ahmedabad, as a research associate, where she was involved in analyzing the hyperspectral and high-resolution remote sensing planetary datasets to comprehend the mineralogy and morphology of volcanics and impact features occurring over the lunar and Martian crust. Whether it is the first time reporting an caldera on the surface of the moon or putting forth a theory for how a mare basaltic region would develop over the time and space, her accomplishments in the field of planetary science are quite commendable. She has recently been involved in the scientific analysis of the high-resolution hyperspectral datasets produced by Chandrayaan-2's imaging infrared spectrometer instrument. She is a brilliant scientist and a superb educator. It was an honor for me to work with her for a significant portion of my life. So without further ado, let's welcome our speaker, Dr. Mamta Chauhan. Ma'am, the stage is yours.
Thank you, Sumit, for the nice introduction. A very good evening to all. First of all, I would like to thank the organizer of the event for the invitation. Now, let me start my presentation. Let me first share my screen. Sumit, can you confirm that screen is visible?
Yeah, ma'am, it's visible.
Okay. So my topic of this talk is geological exploration of planetary bodies with emphasis on ISRO's missions. Mainly the planetary bodies I will be including are Mars and Moon. So before starting, let me give a brief introduction about planetary geology and remote sensing. Planetary exploration is aimed to determine and understand origin and evolution of solar system and planetary bodies that includes planets, dwarf planets, minor bodies, natural satellites. How did they form? To understand the nature of the process.
Oh, sorry, ma'am. Sorry to interrupt you. Can you please enter into full screen mode, and also
Okay.
You can keep your camera on.
Okay.
Thanks.
Okay. Is it okay now?
Yeah, ma'am, it's
Perfect.
fine.
Okay. So how we try to understand how did they form, to understand the nature of processes that shape our terrestrial environment. So this is a pictorial representation of our solar system with the sun at the center and other planetary bodies from near to far. The nature of planetary surfaces provide key information about the geological, physical, and chemical structure of different planetary objects in the solar system. So now, in order to explore these planetary bodies, to get scientific information about the different ways to reach them, either by passing by through with the closest approach that we termed as flyby mission, which is a space probe that passes a planet close enough to record scientific data, or enter into the orbit and start orbiting around it. We call it as an orbiter mission. Or reach their surfaces by landing or roving along. Sample return mission has a goal of collecting and returning sample from extraterrestrial location for analysis. To date, samples from Moon's rocks and Earth-Moon have been collected by robotic and crewed missions. So these are examples of some flybys and landing and roving missions. This is Apollo missions. That was a sample return mission, Curiosity, Rover, Mariner, Venera, Chandrayaan 1. And this is the first image of Earth taken from Mars color camera, a Mars orbiter mission. So planetary exploration relies largely on remote sensing and involves acquiring data with many different techniques that involve measurement obtained in the broad range of electromagnetic spectrum, ranging from visible, thermal, and radar regions to determine the surface topography, morphology, morphometry, surface composition. There can be different techniques for collecting these types of observation, and that may include imaging, high resolution spectroscopy, direct sounding, and sampling by planetary landers and probes. A combination of remote sensing techniques from the ground and space has led to a detailed geological views of many bodies in our solar system. So in this lecture, I will focus upon the lunar surface exploration, remote surface exploration of two planetary bodies. That is our planet, nearest neighbor, red planet Mars, and our own satellite Moon. Through high-resolution optical, topographical, and spectral analysis through the various international and Indian missions to get a glimpse of the processes occurring over there and what findings we have obtained from the Chandrayaan 1 mission and Chandrayaan 2 mission. So Moon and Mars have been explored through various satellite missions. Moon has witnessed more than 139 missions till date. Out of them, 53 failed, partial failure were around 5, and 81 successful. First exploration started in 1959 during pre-Apollo era. The pre-Apollo era, that is 1959 to 1968, when the missions like Zond, Luna, Ranger, Surveyor, and Lunar Orbiter was flown. The first mission to surface the Moon, starting from successfully hitting the Moon's surface, was Luna 2. It was a Soviet Union spacecraft, followed by Luna 9. That was the first spacecraft to achieve controlled landing, and Luna 10 became the first mission to enter the lunar orbiter. From 1968 to 1972, NASA launched its manned mission Apollo programs to the Moon. Apollo 8 was the first successful manned mission that entered into the orbit of the Moon in 1968. And it was followed by Apollo 10, Apollo 11, which was the first successful crewed mission that landed on the Moon. Then Apollo 12, 14, 15, 16, 17. After that, there was the current era from 1990 to present. Then various space agencies, including European Space Agency, Japan's JIXA, and Chinese space agencies, and ISRO's India's ISRO, and various other, and NASA. They have flown their orbiters and landers to the Moon. European Space Agency, Smart 1, Japan's Hiten, Kaguya, Selene, China's Chang'e missions, series of Chang'e missions, India's ISRO's Chandrayaan 1, Chandrayaan 2, NASA's Clementine, Lunar Reconnaissance Orbiter, and many other missions have been sent to Moon. Exploration on the Mars is also divided into different periods. During early 1960s to 1970s, Mars was targeted mainly by flyby at short distance to conduct environmental measurements and image the surface from a close approach trajectory. For example, Mariner. Later goals targeted on orbiter starting from 1969. Mars, Viking, Phobos, Mars Global Surveyor, Mars Orbiter, Mars Express, Mars Reconnaissance Orbiter, Mars Orbiter Mission, Maven, ExoMars, and so on. And lander and rover mission from 1960 to 71. The Pathfinder, Phoenix, Insight, Sojourner, Spirit, Opportunity, Curiosity, Mars 2020. Out of the 48, 23 failed, and 3 partially successful and partially failed, and around 25 were successful. Mars thus has a reputation of difficult space exploration target, and only around 45.5% have been fully successful. The challenges, complexity, and length of Mars mission have led to many mission failures. Now coming to India's planetary mission for Moon, Chandrayaan 1 was flown on 22nd October 2008. It was India's first orbiter mission to the Moon from Satish Dhawan Space Center, Sriharikota. It was launched by Polar Satellite Launch Vehicle PSLV C-11. It carried an orbiter and an impactor. Impactor was Moon Impact Probe, and these are the orbiters. The objective of the mission was upgrading and testing India's technological capabilities in space and returning scientific information on lunar surface. And the scientific objectives for providing the high-resolution mineralogical and chemical mapping of the surface of the Moon, search for surface and subsurface water ice on polar regions, identifying the chemical composition, using various Indian and foreign payloads. There were total 11 payloads, 5 ISRO instruments, these are highlighted in bold, and others were from other space agencies. So these are the payloads: High C, SIR, and MQ for mineralogical mapping. High C, high resolution, hyperspectral imaging sensor. It was India's sensor. I will talk about in detail about the resolution of these sensors in detail in the succeeding slides. Then SIR2 and MQ, Moon Mineralogy Mapper. These three were in spectrometer for mineralogical mapping. Then there was Chandrayaan-1 Imaging X-ray Spectrometer, and KICS for chemical mapping. It was a low energy 1 to 10 keV X-ray spectrometer for chemical mapping using characteristic fluorescent X-rays. Then LLRI and TMC, both are Indian sensors, lunar laser ranging instrument, and terrain mapping camera for topographical mapping. Then MINISAR, it was a radar instrument from NASA. It was mainly for search of water ice, subsurface water ice. Then radon, radiation dose monitor experiment for quantitatively and qualitatively characterizing the radiation environment in near moon space in terms of particle flux, dose rate, and deposited energy spectrum. It was from Bulgaria. And then SARA. This instrument was mainly for magnetic field mapping. It was from Sweden. It was neutron and sub-keV atom reflecting analyzer for imaging the lunar surface using low energy neutral atoms in an energy range of 10 keV to 2 keV to map the composition kicked off from the low energy neutral atoms that are kicked off from the outer space outermost layer of the moon surface by solar wind. And then HEX, this instrument HEX was from high energy X-ray spectrometer operating in low energy gamma rays for radioactive mapping of uranium and thorium decay within chain nuclides. And this was a moon impact probe. It was an impact probe from VSSC Trivandrum. It was ISRO's instrument with an objective of landing the probe at the desired location. So these were the various payloads from Chandrayaan-1 mission. And this Chandrayaan-1 mission was ended on 28th August 2009. The failure of the power supply was mainly the reason, and it was due to overheating. Now coming to the Chandrayaan-2 mission, it was a follow-up mission after the success of Chandrayaan-1, ISRO's first lunar mission. It was launched on 22nd July 2019. It was a composite module with an orbiter, lander, and rover. Lander was Vikram and rover was Pragyan. They were mainly designated to test the capability of soft landing on the moon. The mission was equipped with several advanced instruments planned for in situ measurement to explore South Pole of the Moon and to continue the science carried out by Chandrayaan-1 mission and extend its finding for at more refined resolution. Lander and the rover. They were all having 3 and 2 payload respectively. They were planned to perform in situ measurement, but however, unfortunately, they were not successful. Only orbiter is still orbiting in the lunar orbit, and it is having important payloads as IIRS, TMC, class, DFSAR, OHRC, DFRS, XM, and GS2. So this IIRS instrument is imaging infrared spectrometer for global mapping of the minerals. It has high extended range from 0.5 micrometer, 0.8 micrometer to 5 micrometer. Then TMC2, it is a miniaturized version of TMC1. It is for topographical mapping, the stereo camera having resolution of 5 meter. Then class instrument for chemical mapping for detecting X-ray emission in 0.8 to 15 keV energy range and spatial resolution of 12.5 kilometer to examine the presence of major elements, magnesium, aluminum, silicon, calcium, titanium, iron, and sodium on the moon. Then DFSAR for mapping and quantitative estimation of water ice in the polar region. It is a dual frequency radar instrument having in two bands, L and S bands. Then OHRC vital
Hello.
high resolution camera.
Hello, madam.
Hello.
Madam, sorry for interruption. Could you please turn on your camera? It's possible.
Okay. I think it is. I just have to go back side. So now is it visible?
Just turn on. You just turn on the camera. The second left option. Yes, second left. No. Yeah. This one. This one. Uh, yeah. Now it's fine. Now you can present. Yeah.
It's presenting, ma'am. You are presenting. Just put on the slides on a full screen mode.
Okay. But I think it is not coming in. That.
No. It's just go to the slides. Now it's go to the full screen mode.
Okay.
It's full screen.
Sorry. Screen has.
You stop sharing. You stop sharing. Just share the screen.
Okay. Just let me check. Now is it coming?
No, ma'am. It's still not visible. You shared the screen.
I'm just sharing my screen. It is showing. It is sharing. It is in share mode. Not visible.
It's not visible, ma'am. Till. The third button from the last.
Let me check. Now is it visible?
No, ma'am, still not.
You go to the present now button, the third bottom from the right. Okay.
Yeah.
Then click to the full screen. Then
That
click
is clicked. That is clicked, I think.
Select
Your
the screen
entire
first.
screen and window. Right?
entire screen. Select the
Entire
entire screen.
screen.
Shall I join again? I think it is creating problem.
No, I think
You don't have to join again. The connectivity is fine. Whenever you are just go for that present now button, there will be a option that you have to share the entire screen. Just click on that screen first. You there is a catalog on your screen that you have to select the screen first,
That is
then
only
share.
I am clicking. I think it is not working. Let me join again. I think there is some issue in the buttons. See, now it is in mute mode. Let me.
yeah, now it is present. Now it's okay.
Is it visible?
Yes,
Yeah,
ma'am.
it's visible. Just put it on full screen mode.
Full screen mode.
Yeah,
Yes. Hmm.
yeah, fine.
Okay. So these are the payloads for Chandrayaan-2 mission: IIRS, Imaging Infrared Spectrometer, TMC-2 for topographical mapping, class for chemical mapping, DFSR, dual frequency synthetic aperture radar for mapping and quantitative estimation of water ice and polar region. Then orbital high resolution camera. It was very high resolution camera of about 0.25 meters. It is 25 centimeter resolution. It is mm, the highest resolution camera available for the observation of the moon. Then DFSR and XSM for elemental composition. DFRS, sorry, dual frequency radio science experiment to detect high density plasma lunar absorption at lunar atmosphere using X and S band. And then XSM, that is a solar X-ray monitor. It observed the X-ray emitted by the sun in the range of 1 to 15 keV, energy resolution of about 180 eV, and temporal resolution of about 1 second for quantitative interpretation of lunar X-ray fluorescence and characterization of elemental abundance in solar corona. Then we have Chase 2 for lunar exospheric study. It was sequel of Chase 1 that was on board Chandrayaan 1 in Moon Impact Probe. It is a quadruple mass spectrometer with capability to scan lunar neutral exosphere in mass range of 1 to 300 AMU, and resolution of about 0.5 AMU to measure surface um, and neutral species in the tenuous atmosphere of the moon. Now coming to Mars mission, Mars orbit mission, India's mission to the Mars. It was launched on 5th November 2013 by Indian Space Research Organization. It was successfully inserted into Martian orbit on 24th September 2014. The mission is a it was a technological demonstrator. After that, ISRO became fourth space agency to successfully reach Mars. Also made the ISRO the second space agency to reach Mars orbit in its first attempt, and also the first Asian country to successfully send an orbiter to the Mars. The MOM has 5 instruments and was operational till 2022, orbiting around the Mars in elliptical orbit. The instrument on board Mars are Mars color camera, Mars sensor for methane, Lehman alpha photometer, Mars exosphere neutral composition analyzer, and thermal infrared imaging spectrometer. So Mars sensor for methane was to measure and map methane in the Martian atmosphere. Mars color camera, it was an RGB frame camera from the range of 0.5 to 0.7 micrometer to monitor the dynamic events and weather of the Mars. It was a medium resolution camera, around 20 meter per pixel. And then another payload was Lehman alpha photometer to measure the relative abundance of deuterium to hydrogen in the Martian upper atmosphere. And then Mars exosphere neutral composition analyzer, MENCA. It was a quadruple mass spectrometer for analyzing the neutral composition of the Mars in the range of 1 to 300 AMU with a unit mass resolution. Then TIS, thermal infrared imaging spectrometer. It was in spectral range of 7 to 13 micrometer, the 12 bands, and resolution of 258 meter to 55 kilometer. Now coming to Moon and Mars. First, I will start Moon. To just give you a little information about our Earth's only natural satellite. Moon is the second densest satellite in the solar system after Io. It is the 5th largest natural satellite in our solar system. It size-wise, Moon measures about the quarter the diameter of the Earth. Rotation and revolution are same. Moon orbits in the Earth around the Earth in once every 27 days. So it takes approximately 27 days for the Moon to rotate about once in its own axis. As a result, Moon does not seem to be spinning but appears to observer from the Earth to be keeping almost perfectly still. Earth and Mars form a celestial system with a common center of mass and are considered together as Earth-Moon system because of similarity between their formation and evolution. Moon formation is likely to have formed via collision between a proto-Earth and a Mars-sized body, often termed as a Theia, which occurred much closer to the Earth some 4 billion years ago. This impact threw debris into the orbit around the Earth, which coalesced to form the Moon. Moon is atmosphere-less body, and you can see the near side, the side facing the Earth, easily observable, and the other side is the far side. It is an atmosphere-less body. So let's have a close look of the near side and the far side of the Moon. While the near side, as you can see, has several dark patches, these which we call as mare, and are formed by volcanic activity and basically lava plains, which are formed by extrusion of the magma, basaltic lava from the interior of the Moon. The far side and other portion are mainly, besides this mare, are relatively bright and represent the primitive crust composed of an orthosite. These regions are called highland regions and are older than the lava plains or mare and are also heavily cratered. You can see the spots over the highland region, the circular features. And these are the depressions of varying shape and size due to the impact of meteorites that hit its surface with very high velocity and created a hole in its surface, depression-like features. because of lack of atmosphere. Even the lava plays, as you can see, appears to be circular, and they have also been erupted in large kilometer-sized depression that we termed as basin formed from impact cratering, and later on filled by the lavas and circular in shape. The thickness of near side and far side also varies. Far side has a thicker crust than the near side, and its surface therefore displays dichotomy, near side, far side dichotomy. Near side covered mostly by the darker mare regions, and far side mostly by the rest portion covered by the highland regions. This is just a glimpse of the various from the near side of the moon with the various mare basins. These mare Imbrian, mare Frigoris, mare Serentitis, Tranquillitis, Crismium, mare Nectaris, mare Fecunditis. This is bright craters, Aristarchus, Copernicus crater. This dark portion termed as Oceanus Procelum. This is a very prominent crater, Tycho, with its bright ejecta portion. I will come later on with the cratering process. What are these bright rays? The surface of the moon is covered with, it's mostly rocky and dusty, which termed as a regolith. And this is a glimpse of the lava plains, the mare that is composed of lava flows, just like the on the Earth we have basaltic lava flow formed by fissure eruptions. So such types of lava plains are forming these mare regions. These are different types of crater: simple crater, complex crater, and ray crater. So as mentioned, the far side of the moon is heavily cratered. The at present crater population surface such as lunar highlands or more lightly cratered lunar mares is outcome of long history of impact cratering event. It is the most fundamental and dominant process in the solar system. It is a destructive process whereby a projectile impacts the surface of a planetary body and excavate it, resulting in circular depression. Nearly all craters are formed by hypervelocity impact. When a projectile hits the surface of a planetary body with hypervelocity at many kilometers per second, it initiates an orderly sequence of events that eventually results in formation of a crater. When a projectile hits the surface, in the formation of the crater, and this is example of the formation of a simple crater. The formation start with the process when the impactor hits the surface, and it consists of rapid sequence of phenomena which start when the impactor first hit it and end with the last debris around the crater has fallen down. So these are the examples of the craters. This is the crater Tycho that I have shown in that last image. And this is the central peak of the craters. This is again just giving an example of the crater surface of the Mars. This is the Planitia basin around which it is heavily cratered. This is an example of a crater on the Earth, Wolf Creek crater of Australia. So the size of the craters may range from microscopic level to large, thousands of kilometers large basins from as visible on high resolution images, and also from the microscopic pits seen on the rock retrieved from the lunar surface. So these are the examples of the various types of the craters: simple, complex, peak-ringed, and multi-ring craters. I will come in the succeeding slide. I will show you what is the complex crater and what is simple crater. So most of the craters, as we have seen, are circular, although polynomial approximation to circular are also found. So there may be elliptical craters also, elongated craters also, which may be due to low angle impacts. So crater morphology is mainly dependent upon the size, direction of impactor, geological properties of the surface, erosional and degradational processes, if there is an atmosphere in the planet. Lunar craters are smaller than approximately 18-kilometer diameter as simple craters. They are smooth, bowl-shaped depressions with raised sharp rims and well-developed ejecta blanket. Complex craters are characterized by a central peak and terraced rims. Shortly after the excavation process ends, the debris remaining in the crater moves downward and back towards the center, while the crater floor emerges out of rebound of the compressed rocks, which probably led to the formation of the central uplift in the form of central peak. Or when the size of the crater impact increases, it may result in formation of the mountains of the rings that we termed as peak ring craters. After material is excavated, the crater rim collapses and moving outward and thereby increasing the crater diameter, filling the floors, the crater and shaping the wall in the form of terraces, as you can see. In large impacts, as well as the material displaced and the material that is ejected in form of to form that crater, significant volumes of target materials may be melted and vaporized together with the original impactor. Some of these impact melt may be ejected, but most of it remains within the transient cavity, initially forming a layer of impact melt and coating the interior of transient cavity. This is an example of impact melt formed by cratering process. Material ejected by impact cratering process form ejecta deposit distributed outward of the crater rim. Relatively young craters commonly retain bright radial ejecta rays that we call as ray craters, with bright streaks radiating from the craters. The rays are formed by fresh, bright material excavated from the parent craters and bright secondary craters created by the ejecta. These rays, in the case of large complex craters, extend to several kilometers across the lunar surface, and over the time the ray disappeared, probably due to radiation damage. So this is the example of the crater Tycho, where you can see the bright rays. This is illustration of the formation of a complex crater. Intermediate size craters in which central peak is replaced by ring of peaks. You can see the ring of elevated peaks over this crater in concentric shape. So these are called peak ring craters. This is an example of Schrödinger crater. This transmission takes place at about 140 kilometer diameter on the moon and about 20 kilometer on the Earth. At even large scale, the interior of the craters contains several concentric rings that we termed as multiple ring structures. You can see instead of single peak ring, there is a concentric rings of the uplifted features, ring of the mountains, or you can say peaks, giving appearance of multiple or concentric rings. Craters larger than approximately 300 km are termed as basins and characterized by two or more concentric ridges or scraps facing inwards towards the crater center. Lunar surface has around 43 large ancient impact basins that excavated and distributed a large amount of material across the entire moon, affecting the geochemistry of the crust. This map is showing the main topographical rings of the 43 basins of the moon. This is Spa Basin. These are the other basins. This is an example of another yet special type of crater, we term fracture floor crater. These are characterized by prominent and visible fracture systems on their floor, characterized by anomalously shallow floors cut out by radial, concentric, and polygonal fractures, and additional interior features as moats, ridges, and patches of mare material. These are the LROC back images of fracture floor craters, guessingly. These distant type of impact craters typically occur along the edges of lunar mare basin with ages ranging across the lunar history. These craters are easily distinguished from other impact craters by the unique morphological features of the presence of fractures. These are examples of another type of craters, permanently shadowed craters. They appear dark because, unlike on the Earth, the axis of the moon is nearly perpendicular to the direction of sun's light. This result is that the bottom of the certain craters are never pointed toward the sun, with some remaining dark for over billions years. So many craters near the pole are in the permanently shadowed nearly for about 100% of the time. So we term it as permanently shadowed crater and likely to contain water ice as indicated by plumes of water vapor released from the initial L-cross impact that happened on the Cabus crater in 2009. So this is an example of Shackleton crater, which is a permanently shadowed crater, and these are the other permanently shadowed crater, Shackleton Schumacher. These are the LROC back images of permanently shadowed crater. Now, another dominant phenomena after impact cratering is volcanism. So volcanism, this is also an important phenomenon on terrestrial planets and a manifestation of planets' past and present internal dynamics. These are the vast basaltic plains primarily found on the near side of the moons, and they tend to fill the bottoms of very large old impact basins. Huge volumes of low viscosity, high temperature basaltic lava flows has reshaped vast areas and covers over 70% of the lunar surface. They are typically about 500 to 1500 meter thick. They cover nearly one third of the lunar near side, but less than 2% of the lunar far side. And in addition to this mare lava flows, there are other volcanic features also on the moon in form of shield volcanoes, dark mantle deposits in form of pyroclastic deposits, and dome deposits. These are other volcanic features we term as sinus relays that resemble river-like valleys on the Earth. These are formed by lava flows either on the surface, either as a surface channel along the lava flow, which drain or maybe lava tunnels whose roof collapsed. So these are examples of the volcanic features formed by lava flows in form of sinus river valleys. This is another example of volcanic feature, that is evolved volcanic feature on the moon. It is a caldera-like feature. Here you can see the volcanic domes here, North Dome, East Dome. This is Compton-Velkovich volcanic complex, and it is there's a subsidence feature here, caldera. So it is a highly evolved type of volcanic. They are supposed to be absent on the moon, but they are not absent, but they may be rare on the moon. But this types of feature have also been reported on the moon. This is an example of recent volcanic activity that is about 2 to 10 million years ago. Earlier, it was considered that volcanic activity means in recent times moon is volcanically dead, and no recent volcanic activity has happened. But it is an example of very recent volcanic activity. These are irregular mare patches and representative of recent volcanic activities. These are example of tectonic activities on the moons. Moon shows no evidence of having experienced plate tectonics. So mostly the tectonic features are in form of compressional or extensional features in form of wrinkled ridges and lobate scraps, graben-like features, which we termed as release. I'll just come to skip these features and come to the Mars because I think we have to be on time. So now coming to the Mars. Mars is intermediate in size between the Moon and the Earth. It is the fourth planet from the Sun. It is the second smallest planet. The length of one day and night on the Mars is around 24 hours, and however its rotational period is 687 days, which correspond to 1.88 Earth years. Mars has seasons because a planet's rotation axis is tilted related to its orbital axis. The tilt is currently at about 25 degrees, quite similar to the Earth, whose tilt is around 23.5 degrees. Mars has very thin atmosphere. The atmosphere that covers Mars does not have. Excuse me. The atmosphere of the Mars has around 95% carbon dioxide, 3% nitrogen, around 1.6% argon, and some contain traces of oxygen and water. The atmospheric pressure is less than 10 millibar and about 1/100th of the atmospheric pressure of the surface of the Earth. The low atmospheric pressure and temperature of the atmosphere prevents liquid water from occurring on the surface of the water on the Mars in the present time. These are the two satellites of the Mars, Phobos and the Deimos. Phobos is about 22 kilometers. It orbits close to the Mars and takes around 8 hours to orbit Mars. And Deimos is 12 kilometers. It is farther away from the Mars, and its orbital period is about 30 hours. Physiographically, Mars is also divided into two hemispheres that we termed as hemispherical dichotomy, a low-lying northern half that is sparsely cratered and a high southern half that is moderately to heavily cratered with large basin. The boundary between the northern and southern physiographic regions of the Mars do not closely coincide with the planetary equator, but ranges from 20 kilometers north or south of it. Topographically, Mars show a wide height range around less than 7 kilometers as the deepest point located in the Hellas region. This is Hellas impact basins. These are the prominent volcanic regions. This is the large canyon system of the Mars. And, these are the examples of volcanic features on the Mars. Mars is mostly the volcanism on the Mars is represented by lava plains, and besides the lava plains, there are shield volcanoes, which are the large-sized volcanoes. This is example of Olympus Mons, which is about 22 kilometers. And this is the region, Tharsis regions, where the large shield volcanoes are present. Other than the shield volcanoes, there are tholai, domical features, and patera features. These are steep-sided domical constructs, volcanic constructs that we termed as domai and tholai. And these are the patera regions that are low-profile, inverted, saucer-shaped volcanic constructs, and their rim flanks are highly degraded. So these are manifestation of volcanism on the Mars, mostly represented by lava flows, basaltic lava flows, as we can see here in the Ursa Mons regions. And other than that, there are large shield volcanoes, tholai and patera. Impact features are also present in the Mars, mostly the ejecta crater. These are the example of simple, complex, peak-ringed and multi-ring basins of the Mars. The unique aspect of Martian impact crater is the ejecta blanket that surround them, that have lobate shape that differ significantly from the rayed ejecta deposits of the Moon. They show petal-like flow lobes that are believed to indicate the presence of liquid water in the excavated material. Then these are a glimpse of other surface processes of the Mars, which are altered by various endogenic and exogenic geological processes and characterized by extensive impact and volcanoclastic deposits, erosion and tectonic features. Examples of gullies, which are formed by mast wasting, example of delta, sand dunes, outflow channels, which are formed by catastrophic flooding of liquid and most probably water. Then this is canyon system, and this is polygonal cracks formed by glacial activities and the permafrost region. Tectonism on the Mars is also represented by this just like Moon, extensional and compressional features. This is an example of wrinkled ridges, linear relays, dike swamps, and transparent or strike slip fault on the Mars. Now let me come to the our Indian missions. These are the highlights from the Chandrayaan-1 missions. Recent analysis of this multispectral data from Chandrayaan-1 mission has provided interesting results and insights about the lunar crustal evolutionary progresses. These are some of the highlights. The analysis of Chandrayaan-1 data has resulted in discovery of new minerals and new lithologies. For example, magnesium spinel and OOS lithology, olivine orthopyroxene spinel lithology, confirmation of hydroxyl or hydration features, compositional diversity of lunar surface features, characterization of mare basins and highland rocks, morphological and topographical studies, subsurface characterization from radar data, identification of recent tectonic and volcanic activity, detection of tenous atmosphere, chemical mapping of near south southern highlands, and detection of mini magnetosphere. So I will not go into depth with all the results. I will just share the result from the Chandrayaan-1 M-Cube mission. Important highlights from the M-Cube mission. and also from the IIRS mission. So for compositional analysis of any planetary surface crust, we need hyperspectral sensor data. So the view of the top of the planet is because it is the only available information to study the basic formation process and evolution. This fraction of incident solar radiation that is scattered back to the space by planetary surface is a function of wavelength, contain direct information on the mineralogy of the surface soils and rocks. So the from the hyperspectral data, because they contain continuous bands and hundreds of continuous bands. So there's a result in generation of a unique spectra that serve as a fingerprints for examining the minerals. By collecting the spectra from different regions of the planet, the distribution of these minerals can be mapped, and they can help in determination of the composition of planetary surface, that provide information of the origin and geological or geochemical evolution, therefore providing diagnostic information of mineralogy, degree of crystallinity, or the uppermost few microns of the planetary surface. So these are some of the hyperspectral sensors on board Moon and Mars missions. This is hyperspectral imager from Chandrayaan-1. These are the spectral range and the spatial resolution given here. Moon mineralogy mapper of Chandrayaan-1, spectrometer infrared from Max Planck and Chandrayaan-1, spectral profiler along JAXA's Saline Kaguya mission, imaging infrared spectrometer from Chandrayaan-2. Then these are the spectrometers on board Mars orbiters, thermal emission spectrometer TES on board Mars Global Surveyor, then Omega on board Mars Express, compact resonance imaging spectrometer for Mars CRISM on Mars Resonance Orbiter. These are the spectral range and these are the spatial resolution. So not going into depth each of these sensors, I will just jump into the findings from the Chandrayaan-1 mission, and one of the important findings of the water, lunar water. So when compared to the Earth, the bulk moon is significantly depleted in volatile elements that include water attributed to violent impact origin of the moon. While small amount of water was reported in lunar soil returned from each of the Apollo missions, they were generally attributed to terrestrial contamination. And consequently, in the post-Apollo era, the consensus was that Moon was primarily an anhydrous planetary body that contained less than 1 ppb of H2O. But when the results from the Chandrayaan-1 M-Cube mission came, that gives the clear characterization of the water, because water or OH or H2O bearing materials show a absorption feature at around 2.7 micrometer, indicating their presence. So this was first detection of OH or OH clear indication, although from the some of the earlier missions, there were indirect indications, whether it is by mapping of the hydrogen or whether it is by impact probe. But this is a clear detection from the spectral characterization. This is a global map of the moon generated from M-Cube missions. These blue portions show the areas where are characterized by enhanced hydration features. This is the water spectra. This is the normalized spectra. This is continuum remote spectra, and clipped to the this particular range 2.8 to 3 micrometer, showing the characteristic absorptions of the OH, H2O, and water ice. So these are the initial results that indicated the presence of water OH or H2O on the surface of the water, mostly attributed to the exogenic origin. And this is the polar regions that has been analyzed showing means to indicate the lithological preferences of the OH or H2O with particular lithology. So this is an example from Cheek et al. Then showing the area showing high reflectance at around 3000 nanometer in mainly the bright and orthostatic regions. And these are another example of mapping of the OH relative bands depth index, showing the strong absorption of OH in these polar regions. This is water detection from water ice by radar data. The synthetic aperture radar mini-SAR, which was working in 2.2 gigahertz, could penetrate subsurface, and it was mainly designed to transmit circularly polarized signal and receive the scattered signal back. The sense of reflected polarized signal and its ratio to incident signal, circular polarization ratio, that depends on the dielectric constant of scattering material, and therefore its value can distinguish water from the soil and can be used as an indicator of the presence of water ice. So there were many areas where confirmed to having when the presence of water ice was there through the radar data. So most of the earlier examples that I shown, that was example of exogenic water, that water that that was mainly deposited in the from the in the polar regions, mostly attributed to cometry in origin, contributed by meteoroids, comets, or asteroids that contain water, and also by the continuously produced by reduction of lunar oxide by solar wind hydration. So exogenic water. Besides exogenic water, endogenic water was also discovered from the EnCube data. This is an example of presence of OH bearing exposure in the central peaks of various craters and regions of silicic lithology. This was the reporting of the water from the Bullidus crater. This is the from the CPVC regions. That was the strongest detection of OH and H2O features at around 2.8 to 3 micrometer with a bend strength of about 6 to 17% relative to its surrounding. And similar signatures were also found in the other crustacean dome, Henstein alpha, and Theophilus regions. So now coming to the IIRS imaging infrared spectrometer on board Chandrayaan-2, which is a hyperspectral sensor having spectral range of 0.8 to 5 micrometer or 800. You can see 800 to 5,000 nanometer. Designated for mineral mapping to measure the lunar surface reflectance in 256 contiguous spectral bands with a ground resolution of 80 meter and swath coverage of 20 kilometer. This table is showing specification of IIRS sensor. As IIRS senses both reflected and emitted radiation. That is both reflected and emitted component, thermal component, hence its contribution from the thermal component could be observed beyond 2500 nanometer or 2.5 micrometer. This is image cube of IIRS data and false color composite from IIRS reflectance data. This extended spectral range has been utilized for complete characterization of the observed hydration features that were not possible from the EnCube data because of limitation of that sensor up to 3000 nanometer because of thermal issue beyond 2.5. So this instrument complemented that because of presence of broad spectral range. It could be utilized. I will show you the examples obtained from the IIRS data. This is the initial analysis that we have done using IIRS data to check the mineral capability and detection capability of IIRS data. These are the various minerals detected from various regions of the moon, analyzing the IIRS data. This is the spinel characterized by this particular 2000 nanometer absorption feature. These are the pyroxenes reported from various regions. These are again orthopyroxenes, then high calcium pyroxene and olivine. And these are the initial results from IIRS data to detect clear and complete characterization of lunar hydration features. This is the hydration absorption features or OH or H2O absorption features, that is ranging from 2.8 to 3.1 micrometer. Here we can see the 3 micrometer absorption feature of the water, and it's showing variability along associated with lithology, latitudinal variation. So the initial results that were in analysis of Chandrayaan-2 data, IIRS data for the detection of hydration features. and understanding their affinity with the latitude, with the temperature, as well as lithology. So these are also some of the initial results for a complete characterization of annihilation features. A new algorithm was developed to utilize IIRS data for estimating lunar surface temperature from an approximate value of surface emissivity using IR band of the IIRS, and per pixel surface temperature was estimated. This is the whole spectral range of IIRS data, and it is compared with the Apollo and Luna sample missions. And these are these temperature maps generated from the available IIRS data strips, and these were the analysis then from one of the crater, Copernicus crater, showing the variability associated with the temperature and lithology. And these results have been published. Now, with this, I came to end of my presentation. To summarize, recent lunar and Mars missions have improved our knowledge gained from the earlier missions to develop better understanding of the origin, evolution of their planetary bodies and various processes, including surface and atmospheric processes. While MOM was Moon or Mars orbiter mission, MOM was primarily a technological achievement. It has also produced some important scientific contribution published in high impact journals. Chandrayaan 1 provided excellent opportunity for multilateral international cooperation and collaboration, and obtained results has helped in validation of various hypotheses, including global magma ocean hypothesis, confirmed hydroxyl hydrated component, and indicated active lunar hydrosphere and volcanically active and geologically dynamic moon. Chandrayaan 2 orbiter with advanced scientific instruments and had continued the science carried out by Chandrayaan 1 mission. The initial results have provided important results that include complete characterization of lunar hydration for further with careful analysis and detailed analysis, which is in progress and likely to provide better results. For more information, you can visit these websites for data and image galleries and other related information. At the end, I would like to acknowledge our Director IIRS, Dr. R.P. Singh, for his kind approval for this talk, Group Director and our Head, Geosciences Division, Dr. R.S. Chatterjee, for his support and encouragement. Special thanks to Director NRSE, Dr. Prakash Chauhan, with whom I have worked on Chandrayaan 2 data analysis. And also, I'd like to thank ISRO's Chandrayaan 2 Mission Operation Team, Space Science Program Office, and ISSTC site for providing the data in public domain. With this, I end my talk. If you have any question, you can ask. I think we have run out of time, no? I think.
No, it's fine.
Okay.
First of all, thank you so much for the excellent presentation. There is a thorough research on different planetary bodies. Even you are also presenting an era of planetary geology and planetary missions. Even they have a little amount of evolution in technical fields and all that. So basically, right now there is a thing that we are posting a feedback from in our chat box. So I would like to request all the attendees to fill this form and save it as soon as possible. And for the youngsters, we'd like to hear it from you also. And if anybody need any certificates, so they are also encouraged to fill the form. At least save the link with you for the future. So that was a very nice and very descriptive presentation with all the superficial features from Moon and Mars, and as well as the global consensus also there. So there are some questions from some of the. So, ma'am, I have general questions with the view of a student which is basically just came out from a post graduation and wants to work on the planetary science field. So what is the mandatory requirement for a student to join if they want to work in planetary science, and what are the scopes they have in the academics or research institution in future?
Actually, for planetary sciences, that may include different domains. That may be physics, chemistry, biology, astronomy, engineering, even geology. So mostly they require doctoral degree in these subjects, and those also related undergraduate degrees can also seek internship in either of these the sectors that are involved in planetary data analysis or planetary
Ma'am, could you please
exploration.
turn on the camera?
Sumit,
Sorry to interrupt.
uh,
Yeah.
Sumit, my screen is visible.
No, you stop sharing the screen.
Okay,
Just
okay.
turn on the
Actually,
camera.
there was an issue, I think, with the camera and screen. So
Okay.
I will turn on the camera, right?
Yeah.
Okay, okay.
Yeah, it's
Is it
visible.
visible?
Yeah.
Okay.
Yeah, tell me, ma'am.
So I was telling that suppose yeah, mainly the main employers for planetary geologists are academia and government sectors, right? So and there are some private institutions also exist. So mainly, if you go to universities or higher academic institutes, there you can work as both researcher as well as academicians, and also in the other government institutes which are like ISRO, which are totally involved in this planetary exploration. There you can, so in with any background from chemistry, physics, geology, astrophysics, geophysics. You can those who are having these subjects in their undergraduate or postgraduate degree, and also in doctoral and postdoctoral, they can apply for. They can have their career in this planetary field. Depending upon at what stage they are, they can join as an interim. They can join as again the means in researchers or as an scientist or professors, right?
Okay. So there is a question from Shavana in YouTube. So the question is, I would like to, what is the cause of the formation of polygonal networks on Mars? Is it the
Which
ridge
type
or
of
channel?
formation?
What is the cause of the formation of polygonal networks on Mars? Is it the ridge or channel? Also cause for inverted channels, how to identify whether it's a ridge or an inverted channel?
Using altimetry data, molar data. You can go for where the topographical relief will be easily visible, right?
And maybe they can also go for some high-rise data also. So I think
Along with that elevation data, you can combine both high resolution data, high rise, HRSC or CTX. You can drape this high resolution images over the relief that elevation data. Then you can see the topographical variation. So whether it is uplifted or whether it is low relief regions, that can be easily identified.
so with this, I am opening the forum to all the attendees. So if you have any questions, just you feel free to ask or just raise hand.
Any opportunity, okay, Sumit, any opportunity for project staff or research fellow in planetary geology, you can search for the websites. Time to time, vacancies keep on coming from various funded projects with the universities as well as for ISRO's own project. where you can apply for GRF Research Associate. Is that
So,
well?
ma'am,
Yeah.
I have a question.
Mhm.
So I just want to ask that you are mentioning about shadow region on the lunar poles.
Mhm.
So, in terms of doing the mineralogy and composition analysis, so most of the cases we are using hyperspectral sensor data or basically an optical instrument.
Mhm.
So, what are the chances to use these instruments to get a near about or probable compositions from these areas? Because these areas are mostly under the shadow for near about all the time. So,
Mhm.
what can we do to get the mineralogy, derive the mineralogy from these particular regions?
That can be complemented with radar data, and these information can be used in with association with the hyperspectral data and the permanent shadow region, and those regions nearby, they can be utilized for understanding the compositional variation. If the hydration features would have been present, maybe in the form of frost ice, so they may be in the adjoining regions also. So, so you have to map them, you can quantify them, then you can use the subsurface data, radar data, for ascertaining. So, whether what ice is present, so what type, whether it is there or not, for confirmation.
Even if
Mhm.
exactly, even if landing missions would also help
Yeah,
in
yeah,
future.
landing missions, yeah. And there are also other approaches from high resolution data where temperature data, they can be means combined, and combined study can be undertaken, right?
Okay.
So there is a one question.
So
Mhm.
yes, ma'am.
There is one question that in 12th, if our stream is in arts, including geography, then do we have opportunity to research in IIRS in the field of planetary science? Yes, for geographers, you can work for geomorphology. So geographers, they have opportunity to work in planetary science for planetary geomorphology. Mainly for Martian geomorphology, we means mostly geomorphologists are there to analyze the various morphological features formed by various geological process on the Mars. So yes, geography. If your background is with geography, you can continue, and then you can go for higher studies, and then you can be a geomorphologist. You can check the website of ISRO Center and other thing like that is okay. What are the difference between lunar basalts and orthosites and corresponding rock on the Earth? Okay, because there are different erupting conditions, right? So basically, if there is a basalt or an orthosite, the rock will be same. In the sense, its composition will be more or less same. For example, basalt, it is mainly composed of plagioclase feldspar and pyroxenes. So it will be same for the moon as well as Mars, but the elemental composition may different. Maybe the difference in the iron content, titanium content, the mineral content may vary. Similarly, for anorthosite also, sometimes calcium content may vary from the so different elemental content may vary. Otherwise, mineralogically, they are both same, right? And also because of lack of the conditions of oxygen fugacity, they have also some means effect on the slight composition, but basically the important composition that will remain same. Okay. Is complex craters how the central small hill form? This is from
Central
by
small
rebound.
forms.
By rebound, and initially what happens with the impact, the surface is compressed, and then when it try to stabilize, it rebound in form of this uplifted region in the central part of the crater. So this is how the central peak is formed. Why?
And why it is not evenly bowl shaped.
Why it is not? bowl shaped. So
Evenly
with
bowl shaped.
with the increase in this size, the means there is more increased stress on the central portion. So it get rebound, and then when it is modifying the crater rims, they also means modified and take the shape of the terraces, right? So instead of a bowl shape, it is terraced and with a central peak, right?
There is another question from Savannah in YouTube. Is it possible to visit IIRS for research discussion? Since her research is on Mars, CRISM, IIREES, DEM, and CTX.
Yeah, you can visit IIRS anytime. Because only thing you have to place a mail. So you can send a mail and you can visit anytime. Okay.
So, is there any questions?
One question is from Earth only natural satellite is simply called the moon because people didn't know other moons. Okay, so it is, I think, answer to some questions.
No. That is a comment.
With limited budget. One question is, Nirmal, with limited budgetary allocation, how you foresee the success of ISRO future planetary missions? One question came.
What is the question? Yeah. What?
With, with
Limit.
limited budgetary allocation, how you foresee the success of ISRO's future planetary missions?
With the dedicated team.
Yes, of course. That is the beauty. We are sending the lowest budgetary.
That is a constraint, yeah.
Yeah, this is our expertise actually.
Even in doing the planetary science, there is always the questions comes to us that why we are studying Moon and Mars, or Moon or Mars or any other planetary bodies. Does it help by any means to the field of terrestrial geology?
Mainly for scientific exploration, for resource exploration, from both point of view. Moon being the closest celestial neighbor, our closest celestial neighbor, it is most of the processes that have occurred on the Earth. They have been means washed out by the superficial processes. So most of the process they can be means it can serve as a laboratory for understanding those processes. Plus, beside scientific exploration, there is another for resource exploration. They are explored for resources for technological demonstration also. So there are many motives for space explorations. Okay. So we are not wasting time and money.
Exactly.
Right?
So
If we
over
have
to
any,
you, Priyoda.
yeah, I can see another scientist from ISRO, PRL Ahmedabad, Dr. Amit Basu Sarvadekar is here. If you want to say something, you can say. Amit Basu?
Hello, sir.
Hi. Hello. Hello, Mamta.
Hi.
Yeah, it was a nice talk. Yeah, I liked it. Yeah.
Thank you, sir.
Yeah, I don't have any question further.
Okay, thanks for joining, Dr. Basu. And if anyone have any questions, you can write in the chat box, or you can send in email format. You have our IREES email ID, or you can directly mail to Dr. Chauhan. Okay.
Yeah.
So yeah. So thanks for joining us. It's almost 1.5 hours. Okay. So so thank you, ma'am. Thanks for giving us this time. So we are very grateful to you. Hope in future we'll communicate and we collaborate with some work. Okay. Thanks.
Thank you. Thank you so much. Thank you, Sumit,
Thank
Shubham,
you so much.
and
And thank you all
Dipankar, I
to the
think.
attendees.
Okay. Okay. Bye.
Bye, ma'am. See you.